All right, quick discussion on the titration of a weak acid formal lab. So if you've got lab in person or on campus, you're going to go in and you're going to collect your data. When we do this, we are going to take and we are going to add our standardized sodium hydroxide. The concentration of that was on the bottle. You're going to have one of 4 possible unknowns. One of these is going to give you like a double hump on your titration curve. I know that's terrible drawing. The other one is going to be kind of a straight up where you get one inflection point. By the way, your inflection point is right there, which is your equivalence point. Make sure you weigh out the amount that you're required or requested to. You record that, and then we're going to take and we're going to titrate this. Now, when you titrate this, what you're going to end up with is a lot of data. So if we take a look at some data on this one, and this is just a small amount of a student's data. This is the diprotic acid. We know this has got 2 protons on it because we have 2 inflection points. The inflection points are going to be halfway up where there's a sharp pH change. And one way to look at that is to draw straight lines through here and here, and then go halfway up the line that would connect those 2. You could do one here as well, and you could go halfway up. When you do, you're going to find the inflection point is about halfway up that. That is also the equivalence point. The equivalence point, by definition, is the point where the moles of the acid are equal to the moles of the base. This is going to tell you a great deal about what you have in terms of your acid. So first of all, the one I'm doing, again, I took this from one of the students, and they had a number of grams of the acid that they weighed out was 0.1531 grams. They recorded the molarity of the sodium hydroxide here as 0.1121 molar. And from this, we can get a lot of information. So with this in mind, improving this graph a little bit, when you take and you graph this, make sure you include your axis title. So you'd have a pH here, volume of sodium hydroxide added. Make sure that your title on this makes sense. So this could be, Joe's and Karen's titration, just for example. What are we going to get from this? Well, we have to take, and after we've gotten a nice graph, we have to label this. When you label this, you are going to label your equivalence points. When you label your equivalence points, it may not be an actual data point. You need to go halfway up. Again, I draw lines here, and I go halfway up this. And when you do this, these are your 2 equivalence points. So this would be your equivalence point number 1. This would be your equivalence point number 2. Once you've gotten your equivalence points, we can get halfway. We know that if we're titrating a weak, or any time that we have our nice weak, and we add a strong to it, when we get halfway to the equivalence point, we are in a buffering region specifically so that pH is equal to pKa. If we've got our pH equals to pKa, we can go and we can look at our data here. When I look at this, I get a volume of about 15.5 milliliters. And when I get my 15.5, I can go backwards and get my 7 here, 0.25, and about 7.25. So right around here, my pH is equal to pKa. Now, because this is equivalence point 1, that would be pKa1. I could do the same thing here, go halfway up, and I would get pKa2. So we can label where we have our pH equals our pKa. We got to do a couple more things on our labeling. We need to label where we have a buffer. Remember, our buffering region is anywhere between the beginning and the equivalence point. So we would have 2 buffering regions here, between here and here, where those open circles mean that that is an excluded area. So this would be a buffer. In through here, this would be a buffer. In here, we have our strong base in excess. And we need to do one more thing on this one. We need to take and find the moles of the NaOH added. Well, the moles of the NaOH added at the equivalence point here is going to be the volume at the equivalence point of the NaOH multiplied by the molarity of the NaOH, because volume times molarity is moles. Remember, you put that in liters. So this is going to be 0.0155 liters of my molarity, which I've recorded off the bottle of this, 0.1121 molar. And when I do the math on this one, multiplied by 0.1121, I am going to get 1.74 times 10 to the minus 3 moles of my sodium hydroxide. We know at the equivalence point that the moles of the base, which is going to be 0.01.00, excuse me, 174 moles of the base is equal to the moles of the acid. So 0.00174 mole of the acid. Well, if I've got the moles of the acid, when I weighed this sample out, we weighed out 0.1531 grams. This is what you weighed out. If I divide that by the number of moles, I'm going to get that I have a molar mass here of 88 grams per mole. All right, so we're going to get the molar mass. We're then going to look at our 2 pKa. So if my volume at the equivalence point is here, and that's about 15.5, if I go down to my about 7.25, so about in here somewhere, I'm going to get a pKa1 of about, that's 2, and that's about 2.75. And you can actually read that off one of the data points. If I go to my second one, and I go to my second pKa, it's going to be in here somewhere, and it's going to be about 6.2. So then we're going to look at our data, and we're going to take a look at the 4 possible unknown acids we have. Now, our 4 possible unknown acids are these guys right here: potassium hydrogen phthalate, KHP, tartaric acid, ascorbic acid, and maleic acid. Now, looking at this particular set of data, there's none of these have a molar mass of 88 grams per mole. It's way off. I'm guessing that someone put sodium hydroxide from their burette or some wastewater or something back into the bottle, because again, this concentration is way, way off. So pick the one that's nearest with the best matching pKa. So only one of these has a pKa that works. And in this case, maleic acid, you're going to find has a pKa1 off the data of about 1.94, a pKa2 here of 6.22. The first one here doesn't work particularly well, but the second one is spot on. So we are going to assume that this acid is maleic, and we're going to do the rest of the calculations from there. So again, you're going to take your data, you're going to collect it, you're going to graph it, make sure you label it correctly, find your molar mass, find your pKa's, compare them to what they should be. The sodium hydroxide may have been way off. If it is, pick your nearest acid with the best match on your pKa value. When you calculate the original concentration, there's a whole bunch of things, again, you have to do. You're going to have to do your scatter plot, labeling all of this. And when you do your calculations on this, you're going to need to get your molar mass of your compound, your percent error, your Ka from your pKa, and your initial pH. Remember with your initial pH that your volume was 0.1 liters. Because it's 0.1 liters, you're going to take your moles of your weak acid. You're going to get that from the equivalence point. You're going to divide it by 0.100 liters. That's going to give you your molarity. You're going to need your ice chart. You're going to take your pKa from this, and you're going to take the one that you got. And so this one here was like a 2 point something. I'm going to take that pKa. I'm going to go back and calculate Ka. Remember that 10 to the minus pKa is equal to Ka. So I've got an ice. I have a molarity. I can do my Ka. This one's got a small Ka, so it's going to require the quadratic. Use the pKa1 if you've got the 2 pKa's off your chart. And once you've done that, you can take and write it up. This is going to be a one where you need the quadratic if your Ka is pretty large, or your pKa is fairly large. So your pKa, let's say, is on the order of like 5.4 or about 6 or something like this. You will not need the quadratic. And then you're going to go from there and type up your formal lab report. The instructions and the rubric on that are embedded on the instructions in Canvas.